Hello, everyone. Today I'm going to present a case study in pop-up optimization using machine learning. This is the first complete project by Samurai Technology, and we wanted to share the history of building the project and how it all went. But who are we in the first place? We are a group of people who want to build engaging machine learning products. And by engaging, I mean having positive impact, whatever this might mean. We have already finished our first project, the Smart Pop-up. We are halfway through the Stack Overflow NLP, which I will mention at the end. And we have hosted some meetups in Warsaw and Berlin and are coming to London on 17th of January next year. Of course, you're all invited to join. About the team. The team consists of members of versatile backgrounds, all coming from top Warsaw universities. We have experience in insurance, aviation, investment banking, and marketing technology, which creates a very broad scope. We have different points of view, and all of the members can add something valuable to the project. But after the brief introduction, I want to say something about what we actually did. I suppose all of you encountered the problem of pop-ups appearing during you browsed the web page, you wanted to do something really quickly, and then your workflow was interrupted in a moment. You had to stop, and actually you got angry. I suppose all of you had the situation. Pop-ups are annoying. According to the Nielsen-Norman Group survey, they are the most hated advertisement on desktop computers, and one of the most hated on mobile devices. However, there is another side of the coin. They are quite effective. They bring conversion rate of average conversion rate of 3.1%, which is actually really high compared to what our partner could achieve. They bring relatively high click-through rate, and whenever a pop-up, for example, prompted the user to enter an email, they deliver the results immediately, which is really important. Finally, they're really, really easy to implement. What was our case? We partnered with a VC-backed software as a service platform for workflow scheduling, and they had a pop-up which appeared whenever the user exited the web page area with their mouse, so really often. They had a conversion rate of 1.5%, which is really low, and received tons of negative feedback. They wanted to change it. We saw a slot for a machine learning solution, so we teamed up to make things right. How did we solve this? We host an API with 2 XGBoost modals in the backend. We trained them on user data. And the first one, called the initial modal, was trained on information available at page entry, meaning language, device, some session information, referrals, etc. And the other modal, called the activity-based, used everything that was used by the initial modal and Google Analytics events, which basically mean interactions with the web page. The target was binary. Conversion, no conversion, which was the information whether the user saw the pop-up. There was a place to input their email, and the user was marked as converted if they clicked a submit button. Now, imagine there is this web page with the pop-up logic, and a new user comes. The user is flagged as show. The flag is a Boolean variable which determines whether or not to show a pop-up to the user at page exit. At the beginning, we gather the initial information, this language, location, etc. We send a call to the API with the initial information. The first initial XGBoost modal returns a prediction, a flag update, and the user's flag stored locally is updated. Then afterwards, the user starts to browse the web page, interact with its elements, clicking buttons, and generating Google Analytics events. After every event, we gather the data up to the certain point in time, push everything to the API, and get a flag update as a result. And this is done after every event. one time, second time, third time, and so on. Well, at a certain point in time, the user decides to exit. The user moves the mouse outside of the web page area, and then the flag stored locally is checked, and the pop-up is displayed according to the state of the flag, whether it marked the user as wanting to see the pop-up or not. Now I have introduced you to the business logic of our tool, so I will show several insights that come from building an online ML-based application. The first lesson is, imagine that you have to build a solution like that, and actually you sit down with your team for a while and think about a brilliant solution. After several meetings, you finally come up with something which you deem really interesting, at least in your view. But it happens that this solution does not make use of all the data available. And what is more, compared to other models you're able to train, is suboptimal in terms of prediction. This actually happened to us, and we went through 3 iterations of our business logic. So the first idea was to, the slide is trimmed, sorry for that. The first idea was to train the initial model and sequential models based on events up to 5th, 10th, and so on. So we would gather the information and call the API after each 5th, 10th, and so events. The problem was that it did not make use of the total number of events as a predictor, while actually the information stored in this variable would be transferred to the prediction, masked by the sequentiality of the models. It was not used as a whole. Plus, the concept seemed a bit overcomplicated to us. So we trained the model locally using the total number of predictors, the total number of events, and actually it mopped up our AUC by 0.1, which is a huge improvement. So from then on, it was a must for us to include this variable. So then we decided to reprise our business logic. The next thing we decided on was to call the API between the user exits the web page area with the mouse and before he closes the web page, which was actually not really going to work because there were many questions about the internet connection, about latency, about random API crashes. So then came the third solution, which preserved, and this was about keeping the flag on the user, which I mentioned before. And actually, this solution did incorporate the total number of events as a predictor, was robust against any problem with connectivity or API crashes or anything that could happen, and had larger predictive power. This sentence might sound a bit uninspired for a conference like this, but I wanted to say something about getting to know your data when you try to host an ML-based application and use that in production, and it actually gets a bit harder. Because if you don't get to know your data, then something like the thing on the left can happen. This is, of course, some problem with the label correlated with some predictor, which turned out to be true in the initial model. Because I trained some random forest to look for a benchmark metrics that I can get with no preprocessing, no feature engineering, and so on. And then it turned out that in the large number of Google Analytics events I had, like 30 or something, there was the very event that defined the label. So that was needed to be excluded. This is connected with the first point, that we need to watch for data in a training set, but unavailable in production. By that I mean anything that becomes available when the user actually closes the pop-up or clicks the submit button. This is too late for us to use it. Moreover, there need to be clear imputation rules that need to be passed to production. Any most frequent categories, any medians, any k-nearest neighbors methods that are used to imputation all need to be served and work well in production. Moreover, values of categoricals unseen in the training set need to be handled properly. This is usually done by assigning, for example, the least frequent values to a other category, and then classifying incoming unseen values as this other category, and the modal then is able to recognize it. The last thing is, if train test split is performed correctly, then the same processing pipeline should work for our test data and for real data in production, because we need to perform the train test split at the very beginning to not allow any absolutely 0% of data leakage. Any one-hot encoding before the splitting or anything like that, we need to do it correctly. Okay. Now, another thing about pre-processing our data, we had some features that we were not able to do anything with really quickly. They had tons of different categories, so actually we looked for a way to include them in the model to not lose this information. So we went for something really simple: word embedding, word to vec, namely, as the simplest of them and one of the fastest working, which is important in the production environment. As a reminder, most of you probably know this, but word to vec was introduced in a paper by Thomas Mikolov in 2013, and it actually is about mapping a dictionary of words to a linear space of arbitrary dimension. And what is really nice about this algorithm is that it preserves linear syntactic relationships between words. And this can be seen that if we take a vector from walking to walked and add it to swimming, then we should obtain something which is close in cosine distance to the word swam. But the more interesting thing is how we use that for our data. So we had some three predictors. The first one was some source of the user, from where the user accessed this size. Another one was the internet provider. And the last one was actually the institution that the internet connection was provided to. So in case of residential buildings, this did not give us much resolution. But in case of institutions, private institutions, public institutions, this was really nice because we could tell if this is a bank, a university, a construction company, or anything like that. Then we processed it with a word-to-vec modal, embedded in a three-dimensional space. This 3 was a hyperparameter that we tuned during grid search. And actually, we used the standard implementation in GenSim and used the CBOW because it worked better. And CBOW is actually told to be faster than the Skipgram version. And actually, this worked really well. However simple this might be, the combined variable importances of the 3 new predictors would be the second best in our model, and it brought our AUC up by 0.03. So that was actually worth it. So now we have a preprocessed data set, cleaned and so on. So now we can pass to training our models. As you remember, we had really, really low conversion rate of 1.5%. So this actually fell into the bucket of class imbalance. And this is a really bad thing for most ML models because actually, most ML models need the classes to be roughly balanced because high values of metrics could be achieved by omitting a class altogether. For example, in this case, if we omitted the positive cases altogether, we would get 98.5% of accuracy, which is not good. The standard way to cope with that is to undersample the most prevalent class so that the data set is more balanced. But in our case, this was impossible because that would lead to training the models on several hundred observations, which would not work simply. So we did another thing. We scaled the loss. Here you can see the loss functions that we minimized during adding the test regression tree to the ensemble in our XGBoost models. So actually, we try to minimize some form of distance between the actual label and the prediction from the T-1 trees in the ensemble already, and optimize it over a space of new trees that are to be added. Here is the standard regularization term, which made XGBoost so popular and working so much better than standard gradient boosting. And actually, we have these omega i's, which can be totally arbitrary and chosen by some business decision. But we chose to bring the loss for positive cases up, so that misclassifying a person who wants to actually see the pop-up would hurt much more. The problem with that is that we can use it for a single modal with some specific set of hyperparameters, which also need to be tuned, and also the imbalanced classes problem need to be taken into consideration. So what we did is that we considered the grid search a bit and searched for a good metric to optimize. There is a standard confusion matrix. We have true negatives, false positives, true positives, and definitions of the most standard metrics that we can optimize. Accuracy, but sensitivity and specificity are a bit more interesting. But actually, one must consider what part of the cases are positive. In our case, this was 1.5%. So a modal choosing never to show the pop-up would attain accuracy of 98.5% and specificity of 100%. And actually, such a modal is unacceptable. So now we, of course, we checked optimizing AOC, optimizing precision, and so on. But we ended up optimizing sensitivity, which is the best metric. It returned the best results. But actually, optimizing sensitivity is really sensible from a business point of view, because in our case, this actually is the proportion of people wanting to see the pop-up and classified as so to all the people wanting to see the pop-up. OK, I'm slowly coming to the end. So now, here you can see our final results. Cross-validated AUCs for both modals. And the nice thing is that when you look at the activity-based one and look at the top around here, is that if we choose the probability threshold for us to land somewhere around here, we can attain a really good sensitivity or true positive rate of almost 1, like 0.9 or something like that. And on the other hand, our specificity would not be so bad. And this actually was our goal, because we wanted to retain the conversion of the users while limiting the number of negative, the amount of negative impact. But on the other hand, any reduction of negative impact would be beneficial for our client. So they accepted that, for example, we cut the people not wanting to see the pop-up and seeing them in half. They did not require us to, for example, to make it absolutely perfect. They wanted to limit the negative impact while retaining conversion. We have the models in production for some time. The time is shorter than we would hope for, but actually we were already able to gather some metrics. So now in production, the conversion rate for people who saw the pop-up is 7.8%, which is nice, but we need to remember that the group of people which are actually shown is reduced, is already pre-processed by the model. But the nice information is that the overall number of conversions over a month did not fall. So actually, we did not do any harm to the business, but helped to reduce the negative impact. What else could be done about this model? We could use web pages with larger user volumes, which have more data. We could apply more sophisticated models. For example, imagine anything like a bank or an insurance company. Moreover, we could use multiple web pages. And then, for example, apart from using data for a specific page, we would use the pop-up or the page layout, embed that as an image into some space, and use that as a predictor as well. And moreover, we could do some more precise event sequence tracking. because in our case, the events appeared pretty rarely because it is straining for the device to send requests to the API each second, for example, because that would waste our internet transfer on a mobile device. But having more events would allow us to see some sequence and, for example, apply recurrent neural networks to this. Finally, we were not able to host the machine learning part of the modal online because we had to sign an NDA, but the web application part with some dummy modal included is actually hosted online. So you're all welcome to visit the Samurai Technology GitHub, and there you can experiment with what we did in case of hosting the modal online. And now the final part is what is on the horizon. If you wonder whether it is worth to follow us on some social media, we are starting a first commercial product with iSolution, a software house, somewhere at the beginning of 2019. We have already begun an NLP project where we will try to predict the number of upvotes of Stack Overflow response to a question, so that you can input some text and check whether it will be valuable for a discussion on Stack Overflow. And the next project, this is a bit funny, and this is about what I said in the beginning, that we want to make solutions that have some positive impact. Positive impact would be just fun in this case, because I suppose most of you have played the great game Deluxe Ski Jumping, this pixelized thing. And it is simple enough that we thought that we might try to apply reinforcement learning to that, so that this small guy jumping on skis just crashes, firstly in the beginning, but later learns to jump properly. And finally, there is this London meetup on 17th of January 2019, to which you're all invited, of course, but I suppose we are sure to host some meetups in Warsaw and Berlin in the first half of 2019, to which we also invite you. That's all for today. These are some contact informations. Please, if you have some questions, do not hesitate to ask us. Now, thank you. That is all for today, and I invite you to ask me any questions you want.